privilege and pride to introduce one of your classmates as a speaker, next speaker. So Dr. Madhuri has been my colleague when we did advanced diploma in bioinformatics, and then he further went on to do his PhD at University of Groningen and his postdoctoral at Netherlands, and then he is currently working with Wockhardt as a research scientist and is involved in the implementation of accurate procedures for biosimilar characterization, identification of pitfalls in this characterization methodologies, and he is instrumental in authoring and reviewing the regulatory filing procedures as well for the company. So now the title of his talk is STP Development Challenges Using AUC for Recombinant Protein Aggregation Profiles, and I guess this is of interest to most of us, and I invite Dr. Madhuri to give his talk. Thank you.
Thank you very much, Annama, and it has been a great privilege to back to this academia world after a long time actually, and being a speaker, it's really interesting and enthusiastic to speak to you all people. And yesterday we had a great demonstration about the AUC technique, and there were a lot of challenges. People were discussing a lot of, especially about the data analysis actually. So, I mean, yesterday there has been a lot of discussion about the absorption profiles in the AUC, but I thought today we will focus on the interference data, and that's a challenging we resolved recently, and we came up with nice data actually. But I will not speak about complete data, but I will share the challenges what we faced, and how different parameters we can include to refine the data what you observe actually. So the title of the talk will be a little bit different what Annama has said. It is STP Developmental Challenges Using AUC for Higher Order Structure Analysis. I changed a little bit the topic because that is much more compatible to what I want to say actually. So the outline of the talk is divided into a few things, and the first thing will be the complexity of the protein analysis. So why there is a more complexity in protein analysis, and why should we do a different biophysical characterization to analyze what we want to see in terms of protein function, structure, and how it's related to these protein-protein interactions actually. And there are a lot of different structure analysis tools in the market available, but I'll be focusing more. Is a pointer? Which is a pointer here? This one. So primarily I will be dealing with, so just very close. So I'll be dealing with the basics of the interference optics system that is present in the AUC, and the various complications you have in execution of this SV interference. And I'll be focusing a few slides about the data analysis and what is good data and what is bad data in terms of interference data, and conclude with a conclusion. I feel for myself the proteins generally have a lesser framework, but it is more complex. Why do I say this is a lesser framework? In the sense that if you take the secondary structure elements in the protein molecules, there are only few, like helix, beta strands, and the loops. But it generates a huge different structures as such, and it becomes more complicated for us to analyze it as such. But so what we are interested in understanding this protein structural analysis is that we try to investigate this secondary structural content, which is alpha and beta strands, and then we hook on to the protein structural features, whether this is an extended globular type of features, and we want to truly understand the oligomeric nature of the protein molecule. And this is a very important characteristic feature. And apart from that, by combining all this, So by combining all these features, we tend to understand the protein-protein interactions as well as the protein-ligand interactions. So taking this into account, I came up with a small sentence which I feel for me it seems to be interesting actually. So with a single technique, enigma of protein structure and functions cannot be resolved. But analysis correlated with diverse experiments serves to unravel the inner beauty of the protein molecule. So the protein structure itself has different degrees of structural organization. It carries from the primary structure, secondary structure, tertiary structure, and quaternary structure. So it has a plethora of information in the protein molecule as such. So while studying or investigating the protein molecule as such, we go across different techniques depending upon the level of the study you are doing actually. For example, the primary structure, you take the protein sequencing in LCMS, and if you want to investigate the secondary structure, you probe with the cyclodichorism or FTR studies, and if you want to probe the tertiary structure, you have different techniques. And sorry, I missed here the differential scanning calorimetry here, and you want to probe the quaternary structures, you have a different techniques here. And my assumption was that, it is very close to this particular thing, and so the more the complexity of the structure goes, the technique complexity also increases, and as well as the data processing and analysis also becomes more complicated. Taking the complexity of analytical ultracentrifuge, I'll be focusing more on interference optics actually here, and already most of the people yesterday have seen how the analytical ultracentrifugation runs actually operates. So we have a small sector shaped cell in which you place, in which you place a respective solvent and the sample, and you spin at high centrifugal forces. So what happens during the spinning process is that you create a concentration gradient along the radius, and this is a principal fundamental aspect of the analytical ultracentrifugation. So while you generate a concentration gradient along the radius of the cell, you have a vertical fringe displacements. Let me explain you what is vertical fringe displacement in the next slide. So in short, what happens in interference is that you have two sources of light, source 1 and source 2. If these two sources of light are in phase with each other, there is a constructive interference. And what do you mean by the constructive interference? That the two lights wavelengths are similar, and when they combine, you see an increase in the amplitude. And this increase in the amplitude is reflected in terms of increase in the intensity actually. And on the other hand, if you have two wavelengths, two waves differing in the phase with each other, they nullify each other, and you don't see a maxima in the intensity. So this is what happens actually in the interference pattern, and it is also the schematic diagram that is present in the AUC also. So you have slits, and you have a source of light here that is passing through the one slit, which has become much more coherent, and in order to increase the coherency of the light, there are two slits placed, and this coherent light and from these two slits interfere each other, and during this interference, during this interaction process, you have this constructive interference as well as the destructive interference, and this phenomenon facilitates you have the maximum intensity and the minimum intensities, and this maximum and minimum intensities in the AUC we call it as fringes. And in the AUC, the sample sector, what I shown before, is placed in this path of this coherent source of light actually here. And when these two light source passes through the two different solutions, one is the reference cell and one is the protein cell, you have a change in the diffractive index of the sample. And the change in the diffractive index of the sample will produce a change in these fringes actually. And we call this as a vertical fringe displacement in terms of AUC. And these vertical fringe displacements are very difficult to interpret in terms of AUC. So what they have done is that they have introduced a fast Fourier transformation. This is a mathematical transformation of your complex wave pattern that gives a curve similar to this sigmoidal curve, which is nothing but a fringe displacement. And mind you, this is completely different from what we have seen yesterday from the absorption profile. This is only the fringe displacement of the solution, or change in the refractive indexes, what is happening in your solution is represented in terms of the fringe displacement. So it is completely different from the absorption profile what you have seen. This is very important. The fringe displacement is recorded over a period of time, along the radius of the cell actually. So, and fringe shift is directly proportional to the change in concentration in the sector cells. So, as you spin along the cell over a period of time, the concentration gradually changes and it always increases actually. And this increase in the concentration causes the change in the refractive index tremendously, and this fringe pattern also changes, and that is what you are going to record primarily in the AUC in case of interference optics. So, taking all these factors into consideration, and also I have gone through different complexities or the complications people have faced in running this interference data. There are a lot of different parameters I have summarized here actually. So, the first one is a protein concentration. So, what is the right protein concentration? That is the question that has been asked yesterday actually. I mean, this is an experiment where you don't have a rule of thumbs actually. I mean, you cannot say which protein concentration is the best one to really work on it actually. So, we have to go trial basis to see which is the best concentration to work. And apart from that, the most important characteristic feature is that the zeta potential. Yesterday we have seen in case of DLS presentation, the higher the zeta potential value, you have the higher charge surface on the protein molecule. That means when you are concentrating this type of molecules in a solution, the tendency to come towards each other is very, very less because they have a higher zeta potential value. Yeah? And now when you are working with this type of protein samples in an interference or any other analytical centrifuge, because the protein molecules are coming very close together, you have a tendency to create turbulences in the solution itself, and these turbulences create a lot of noise, especially in the analytical centrifugation. So you have to really play with different concentrations way to minimize these type of interactions in the protein molecule in the AUC. And this is also one of the critical feature of AUC experiment, because you have to really see which centerpiece you have to use. And this also produces, type of centerpiece also produces a lot of noise in the AUC data. And assembly is also one of the most important feature in the assembly in the AUC experiment, and if you mess up anything in the assembly process, you will have a lot of noise in the data. And also the speed, as I told you, the proteins, I mean, if you have a different the charges on the protein molecule, I have to really work out with the speed, because you have to come up all the protein-protein interactions in the solution, and these interactions can create turbulences in the centrifugation process. And the volume of the reference in the sample cell. In the case of observance, most of the people know that you should have differences in the volumes of the reference and the sample cell. But here in this case of interference experiment, you don't have to have the differences in the volume. Why so? Because we are working on the fringes, not on the differences in the solvent and the sample reference. Because when these fringes are calculated based upon this initial fringe references actually. It doesn't take the account into the meniscus, sample meniscus. So you don't have to worry about the meniscus actually. The only way you have to ensure that the volumes are equal. Because if you have a differences in the volume, that will affect your path length of your light. And if it is a path length difference is occurring, and then your the fringe displacement will occur actually. So this will add again a noise to your sample. So we should be really careful when adding this volume of the reference and the sample while conducting your AUC experiment, especially the interference data. And the time interval between the scans. And this was also the question yesterday has been raised actually. What I feel that, I mean, in this case, a time interval between the excisions, I feel if you are performing the sedimentation velocity experiments as such, I mean, I leave it to 0, because I want to track all the events that is happening during this sedimentation process. And also this is a variable actually. You perform different experiments and then you see whether you want to have acquired all the data or not. It depends upon the protein behavior in the solution as such. And the most critical part is the data analysis as such. We will see how the data analysis can be done. And the next is the type of placebo and the reference, and this is a critical aspect also, because we have a reference cell and the sample analysis, and most of the people know about that actually. And this is yesterday I found this paper very interesting actually, and they've been focusing on the complications of the AUC. And so they say clearly the precision of the SV AUC is influenced by the numerous factors. For example, the sample characteristic features, the cell alignment, the centerpiece quality, and the data analysis approaches. So, but improved analysis technique improved methods of accurate align cells to the center of the rotation, and high centerpiece quality can dramatically increase the overall precision of the measurements. So it is the analytical person who handles this instrument has to be very careful for the initial stages in order to provide a useful data of the AUC. To show you the live data, this is where the data we started to interpret actually. This is the initial experiments that were done before I joined Wockhardt actually. And from this already you see there's a lot of noise in the data, and there's no clear baseline I have seen here. And also you see a lot of, already the baseline has been, or the sedimental molecules has been sedimented actually, but in spite of that there is a lot of noise, and they could not able to really correlate your experimental model as well as you apply the Lamb equation in your analysis, and they are not fitting actually each other. And that is clearly visible in the case of residuals, and you don't see any real pattern actually here. And you see the residuals are a very high value of around 2 value actually. This clearly indicates there is a lot of differences between your experimental observations as well as the model predicted sedimentation values actually. And this is another way of looking at the data actually. So this is called as a bitmap analysis, and this is analysis where the noise has been modeled on the rows and columns actually, and if there is any discrepancy in the noise, you see a strong diagonal line. You see a strong diagonal line across it actually, and the residuals. And the residuals means that the differences between your experimentally observed values to the modeled values. So there's a large deviation. You see a great color here, and that's easily visually it is very clear that there's a lot of differences between your experimental and observed values here. So this is a better way of interpretation of your data. So I strongly recommend taking the residuals aspect in terms of analysis as well as the bitmap analysis that give a clear picture where your data has been properly working actually. So I showed you already the different parameters that has to be taken account actually. So we implemented a lot of factors sequentially changing which one is the best result actually, and we came up with a nice sedimentation profile. In the first graph, you see clearly the sedimentation profile is really nice, really clear actually, and we don't see any imperfections in the data. But I told you the residuals and bitmaps still give a clear picture for you what is happening in the data. Here you see a wavy-like pattern actually. So what people say is that if we want to have a clear demonstration of the fitting between the observed as well as the experimental values, the residuals should be randomly distributed. There should not be any systematicity in the residuals. And now we see a systematicity in the residuals that still indicates there is a noise in the data somehow. And it is clearly visible also here. So there's a diagonally, you see a stripe. That means the noise, there are two different noises actually here. One is time independent systematic noise, that is because of the optical imperfections you have, and whereas the other one is a radially independent systematic noise because we are calculating the fringes from the Fourier transformation. So there is some noise available from this fringes calculations actually, and if these two are not properly corrected, then you have differences between the noise levels, and then the strong diagonal stripe that is occurring on the bitmap is visible actually. But this is good to have this improvement because we don't see those red blobs of pictures here, the before slide what you had actually. So we could able to reduce a lot of noise by incorporating many parameters what I've shown before. To have a more visual impact, we have used the Goosey software that is available freely to all the people actually. So there the same, the previous slide data have been modeled here. You see clearly the experimental values that is represented by the dots clearly matches with the modeled values actually. So this first gives a clear impression that whatever you have done is nice. But if you go to the residuals part, you see a wavy pattern actually here. So there is something still, a noise available in the data that we have to refine it. So based upon our continuous working, we have come across some parameters that really affects the noise removal. So we implemented those parameters and we have come up with again improved data here. And you can see clearly the residuals. There is no systematicity in the residuals. It's all randomly distributed. And also the values has been decreased tremendously from 0.04 to 0.01 here. And further optimizing this, still you could able to manage, still reduce these residuals from 0.01 to 0.02 to almost to the baseline actually. And now here the bitmap is almost, the diagonal stripes are completely gone and it's much more clear. So, based upon our expertise and experiences of working with interference and also by having the demonstration from yesterday, what I feel that all the improvements in all the experiments, I think there is a clear experimental cycle can be developed actually here, where the user has to be trained properly in all the techniques and he has to know what has to be done properly. And once the experiment has been executed, the data analysis is a very critical part that facilitates you to improve or inculcate new parameters to optimize what is needed and what is expected. And you incorporate them in the improvement cycle, and then the cycle continues until unless you have scientifically accepted data. And I'm really thankful for the small team that I have here, and most of the work has been done by Vasundhara actually, and I would like to thank Dr. Amarnath for giving the opportunity for me to express my expertise here in front of knowledgeable people here, and thank you for your attention.
Dynamic in nature, do you think the residual content what you showed would come at a higher level?
It's all the dynamics of the proteins. I mean, I don't know what protein you're speaking, but if you have a lot of protein-protein interactions, and if you look at the zeta potential values, and if it's very high, then I think you have to really play with the dilution process and then see where you can reduce the residuals in your picture. What we call in the scientific terminologies, these are called as macromolecular turbulences.
So that will stay as a feature of the interference or the plots you showed at the end. In one of your slides, can you just go to one of your slides? Even further? Yeah. So the middle one, if you see that you talked about the residuals there, right?
Yeah, I mean in all the pictures, whatever you have in the AUC, you have a different way of analysis. You have a residuals, you have a bitmap, and you have an histogram also. That's also a nice way actually. So if you integrate these three and you have a collective pictures of what is happening about the noise, then you can really optimize the protein sample as such.
So just for the sake of better understanding, if I have a protein which is say fairly unfolded versus a protein which is more folded or structured, do I see a pattern of residuals there?
If you say it's unfolded, I mean, I don't know how the centrifugation process will, or the molecule will sediment actually. I mean, it will sediment or not, I don't know with the centrifugal forces what we have actually. But definitely we will expect differences because when you compare the globular protein and extended protein molecule as such, I mean, there are differences in the centrifugal forces you apply, and I mean, I think there will be definitely changes in the noise levels, and because in that aspect, I mean, in the case of unfolded proteins, you should really see the sedimentation is reached to the bottom of the cell. Otherwise, this back diffusion process occurs, and then it creates a problem for your analysis. Actually, I mean, yesterday there was a colleague who was showing the data to me actually with 1.3 kD protein, and the forces he applied was huge enough, but still it did not sediment completely to the bottom of the cell. That means at a certain part of the cell, it has reached all the forces are in equilibrium, and the speed that is generated cannot pull the protein back to the cell actually. So I mean, there are certain limitations on it also. So it's a protein dependent thing actually.
Thank you.
So thank you, Pramod. It's nice presentation. So if I have two instruments, one is AUC and the other one is triple F. So which instrument would you like to prefer?
Both.
Why?
It's an orthogonal technique, so sometimes you cannot resolve all the issues what you have with one instrument. For example, now here we are subjecting a protein molecule to high centrifugal forces. So you don't know what happens in the shear strain, your protein molecule might dissociate, something can happen actually. So you want to correlate your experiments with the triple F. Triple F don't have any forces actually, you apply the sample and it's also column-free environment. So that maybe the resolution is much better, maybe you can see the true nature of your protein molecule as such.
But when we have the highly complex maps, and if you want to identify whether it is soluble aggregates or insoluble aggregates, and a couple of questions on the density parameters, but when you select the triple F and you have more choice to
Definitely.
set your temperatures and density and other parameters.
That is the major advantage you have with triple F.
Triple F, right?
Yeah. I strictly go with triple F if you have this different aggregation behavior.
Exactly.
Yes.
All right, thank you.
Yeah. It's a choice you have to make depending upon what you want to have actually, based upon instrument settings and everything. But for example, in a case of aggregates, you say temperature dependent, you cannot do it in AUC actually. So I advise strictly go for triple F studies then.
Yeah, nice presentation, Dr. Pramod. You have shown some interesting data here. The slide which is right now shown and then how you have concluded it. Would you like to throw some light on what kind of efforts are being made to get a clean data like how you have shown at the end of this presentation?
Yeah, I was discussing with my manager also. This is critical parameters. You cannot really have a rule of thumb to really improve the data. It is a protein dependent and also depends upon the analyst. He has to be very critical in the data analysis. Change one parameter, analyze what is the influence of that one parameter on the experiment analysis actually. So we cannot have a collective effort. For example, if you have a protein concentration, you minimize the protein concentration and see the residuals of the bitmap, how it are improving actually. So once you optimize the protein concentration, go to centerpiece now. The centerpiece, does it miss the quality of your protein? Are there any interaction in the buffer solutions with the centerpiece actually? That creates any noise in your data or not? So likewise, you have, these are the parameters I have chosen from different articles that are already present in your PubMed actually. I think these are very critical parameters, and also you have shown in the next paper also. This is an interesting paper. I think most of the people are asking about the aggregation. These people have done a lot of studies about the precision and accuracy of the protein aggregation in using the AUC itself. From that you see clearly but analysis technique and higher centerpiece quality control dramatically increase the overall precision of the measurements. So you have to collect all the parameters and see which one is really working, and you have residuals, bitmap and histogram analysis for the noise level analysis actually. If they are very clear and you are satisfied, then you are done. Yes, definitely. It's not consistent among all the proteins. Yes.
Is AUC data and DLS data comparable? Means volume PSD from DLS data is comparable to AUC, or have you compared both the datas?
The AUC I think is more sensitive, and in case of DLS you have a restrictions actually here, because it is an intensity based analysis you have, and if you have an aggregates, very high aggregates, that will influence your the smaller states to study actually. It will mask the smaller states actually. So again you have a restriction there on what you want to study. In case of AUC you can separate these aggregates and easily.
Have you compared both the data? From volume PSD we get proper...
No, I did not compare the data actually, no. In case of the biosimilar studies, what I am doing is now just take this innovator product and the biosimilar product and do this AUC experiment, and if they are similar, do this, because output is different somehow. The sensitivity of the instrument is different here, so you cannot compare exactly the data from both the instruments now.
I'm sorry, you can go ahead directly for the next question. Thanks, Mr. Kumar, for a wonderful lecture.